You're absolutely right to be concerned, and I will not be able to prove Birkhoff theorem in this course because it takes too much time. So you have to go over to math department with it. What I'm assuming here is that everybody in the class who does this experiment will get the same density function. Now, that's not guaranteed at all, and that's why we went through all this symbolic dynamics, etc. So it's obvious that if you have pieces of dynamics that are disconnected, something happening here and something happening here, and the two don't communicate, you will get different averages on these pieces. So this assumes that you're looking at one ergodic transitive component. Now, proving that this limit will really happen is called Birkhoff theorem, and you'll have to get it someplace else. Because that will really derail me in this course. And it has this property of mathematics. It's a beautiful thing, but maybe it's not what you really need. So what saves us is the fact that we really care about noisy systems. Systems that, it doesn't matter how weak the noise is, but slightly weak noise. So we really care about things that are slightly smeared out. So this is the lowest point of the course. At this point, we get to reason why ergodic theory is ergodic theory, and there are journals dedicated to it and nothing else, and there are people who, get very fancy prizes, spend their lifetimes doing it, because it's very difficult to assure that you have systems in which everything is visited the way I draw this picture. Could be very, and I can derive perverse pleasure from it myself. I shouldn't spend too much time on it, but if you give us enough money, people on the 5th floor, and you tell us, I would like to find a stable solution of Navier-Stokes equation such that after 1,027 hours, I realize that I'm back where I started and this is not unstable. If you give us enough money, we'll construct such solution just to please you. We'll find them. Because we can find individual, something that a non-system is very good for. We can change some parameter in 6 digits, very specifically in 3 next digits, and we can make a non-13 cycle attracted whose transient time to fall into this hole is 100,000 iterations on general. So mathematically, we can we can design these things. We can design in such a way that you'll never figure out that this is actually an attractor. Only we will know. We can use it as cryptography for fight national security agency. We could really do stuff. So if you do this as a mathematical problem, this is hopeless. You can design any complicated behavior you wish, and once you start understanding how the complication comes in, you realize it's very easy to do, but for that you'll have to pay a high price. You'll have to be extremely precise, your initial conditions. But in our world, things are noisy, and all these magical things get wiped out. My 13 cycle, you'll never find it if you're allowed to compute only to 1% precision, because its basin of attraction will be so small that even if you're there, 1% will kick you a mile away in the units of that attractor.